Hello, Mr. Thomason here. I just want to give a quick review of how we classify matter and also the states of matter with a few examples. So with matter, it's important to, of course, know what matter is in chemistry. And it's just anything that has mass. So things like ideas or songs or something that you can't put on a balance. Even things that have a very little amount of matter, like an electron, are still considered matter. When we're looking at macroscopic things in the real world, it really helps to be able to separate things into categories. And one way to separate things into categories is whether they are a mixture or a pure substance. Most things on Earth and in the universe are mixtures. And a couple key terms that are good to keep in mind is that mixtures have a variable composition, which means that the ingredients, and one example we could use would be, say, noodle soup. It might have a different amount of noodles and water and spices, but still be noodle soup. And pure substances have a fixed composition, so they have a fixed ratio of particles, whether they're elements or compounds. So with mixtures, the components, they keep their characteristic properties, and you can separate them. A very important term here is that you can separate them by physical methods. You could also separate by chemical, but something you can only do with mixtures is separating by physical methods, where with pure substances, you can't separate them by physical methods. All right, so with pure substances, I'm going to start over here. These properties are the same throughout. So if you have sodium chloride salt that is from a rare part of the universe, as long as it is one sodium and one chloride, it's going to have the same properties no matter what. Same goes with elements. If we have gold, it doesn't matter where we got that gold from. That's silver. If it's gold, it will be, as long as it's pure, it's going to be the exact same. Now we'll talk about isotopes later when we get into the inner workings of the elements. So an important thing to recognize between elements and compounds: elements are on the periodic table. So if it's on the periodic table, it's an element. Where compounds are a combination of those elements in a fixed ratio. Here it says definite ratio. I use the term fixed ratio. So things like water, sodium chloride, other examples, those are in a fixed ratio of elements. With mixtures, homogeneous means it has the same composition throughout. And an example of that would be a sports drink, which we mentioned in class. As long as there's no ice cubes floating around or any particles, it's going to have the same composition on the top of the drink, in the middle, and at the bottom. And these are often called solutions. So a synonym for a homogeneous mixture is a solution. And for heterogeneous mixtures, they do not have this same composition throughout. So Rocky Road ice cream, for example, has some parts that are just chocolate, but then you might get a marshmallow or a peanut, depending on where you scoop. So I say to use the spoon test to determine whether something is heterogeneous, where with the spoon test, you'll get something different each bite. And with the homogeneous mixture, you'll get the exact same thing, depending on where, if you scoop from the top or at different places in there. So let's go through a few examples. Carbon dioxide has this fixed ratio of 1 carbon to 2 oxygen. They're chemically combined. This is definitely a pure substance, and it is a compound. So I'll just put a C for compound there. It's made up of more than one element, so it can't be an element. And the reason we know it's not pure is because there's only one type of particle, or a carbon dioxide molecule. The next, ocean water, because it has multiple types of particles and it's in a variable composition, this is definitely a mixture. And because it doesn't pass the spoon test, what I mean by that is with each spoonful of ocean water, you can get different stuff. You could get some sand, you could get apparently pure salt water, and you could also get like a little piece of seaweed or something like that. This guy is heterogeneous. Now that's different from salt water, because salt water is just sodium chloride dissolved completely, and we say aqueous, in water. So if you just have salt dissolved in water and it's completely dissolved, then it's going to have the same composition throughout. So for salt water, it's going to be a mixture, and that's going to be homogeneous or a solution. Gold is on the periodic table, so it is a pure substance. That also happens to be an element. Gold, we know that symbol is Au. Brass is a tricky one. It's actually a solid solution. So brass is a mixture of copper and zinc. So because it's a mixture of metals, as long as they're consistent throughout, so as long as there's the same ratio of copper and silver, copper and zinc, then that is going to be considered a homogeneous. Now, it is true that you could have a mixture of metals like in coins where they're not mixed evenly, but in the case of the trumpet, it's safe to assume that the ratio of carbon to zinc, or copper to zinc, is going to be the same throughout. For number 6 here, air in the room. In the room, you can assume that all the gases are spread out evenly. So it's definitely a mixture because we have oxygen, carbon dioxide, water vapor, nitrogen. And since they're spread out fairly evenly, it's safe to assume that this is homogeneous. It is true if you turn on like the gas jet in the lab, you could get a little temporary mix, but just in your typical room, we can assume that it's going to be homogeneous. Where if you look at in the atmosphere, across a large area of the stratosphere, you could assume, or you could observe, that there are different layers with smog and clouds in the atmosphere. So if you go and zoom out the atmosphere, it looks a little bit more heterogeneous, so a variable composition. Oil and vinegar dressing, there's definitely a separation there where it doesn't pass the spoon test, so it is a mixture with different parts of oil and vinegar and dissolve things in different areas, so this one would be heterogeneous. Since an ice cube is water, and if we say it's pure, we're going to say this is a pure substance. And if there's nothing dissolved in that ice, then we're going to say that this is a compound. So it's just H2O. For tap water, there's stuff dissolved in there. We have some chlorine. We have some ions floating around. So tap water is a mixture. And because it's a consistent composition, tap water is considered a homogeneous mixture. So you're going to get the same amount of dissolved stuff in the top or the bottom of your glass. Now, of course, if you have polluted tap water, that could change things if there's sediment in there, but most tap water we could consider homogeneous. Looking at these particle diagrams, it looks like this guy is a 2-to-1 ratio of what looks to me like maybe hydrogens to oxygens. So this is definitely a compound. And I'm also going to give the state of matter here. This to me looks like they're spread out throughout the box. So I'm going to say that this one is a gas. Here, they're all made up of the same particle. So this is an element. And again, they're spread throughout. So this guy looks like a gas. Here I have more than one type of particle, so this guy's a mixture. It looks like they're spread out pretty evenly, so I'll call this homogeneous. And again, they're spread throughout the container, so let's say this guy's a gas. For D, again, it looks like we have a gas with two different types of particles, so a little bit repetitive, but this one looks like it's homogeneous, mixture, and a gas. With this one down here, it looks like we have a fixed ratio of positives and negatives, and they're all connected together. So to me, this one looks like a compound and a solid. And down here, it looks like we have some ions dissolved in something that to me looks like water, and they look like they're spread throughout pretty evenly. Since I could conceivably have different amounts of those ions, this guy is a homogeneous mixture. And it looks to me like there's some space there. Oh, that's a tough one. For a liquid, I would say they're a little closer together, but I'm going to go ahead and say this one's a liquid, although we could probably argue that one. All right, just quickly finishing this up. And again, you can speed this video up if or even skip parts. But for properties of matter, if we're talking about physical versus chemical, physical means that we can observe or measure without changing the identity of the substance. So if you're taking something's temperature, you don't need to change its identity. So these are further broken down into extensive properties. And extensive means that it depends on the amount you have. So things like mass and volume, those properties change the more you have. So if I have a whole bunch of gold, then it's going to have more mass than if I had a little amount. So extensive means it depends on quantity or changes with quantity. Where intensive means it's independent of quantity. These would be things like density, temperature, and if I have some water coming out of the tap and I just get a few drops, or if I get a huge tub of it, it's going to have the same temperature. Now we can talk about changes to that. Another would be density. If I have just a few grams of copper versus a large chunk of copper, it's going to have the same density, so it's independent. So some of those things would be like, let's say, copper density. All right, for chemical properties, it means you must potentially change the substance to determine the property. For example, is paper flammable? All right, well, the way we're going to check that flammable property is by igniting it, and most paper in most circumstances is going to catch on fire. So we have to change that paper into something by undergoing a chemical reaction. Or if it doesn't undergo a chemical reaction, so it has the potential to change. So if we tried to light, say, gold on fire I'll use that example again. It does not easily light on fire, so we could say that gold is not flammable. And even though we didn't change it, we had that potential to change it by putting it into a chemical reaction. Density is a physical intensive property. It's independent of the amount. This example is a little bit more from our last unit. And the last part to this, physical change. When we go through a phase change, we call that a physical change. So just one particular example of a phase change would be boiling, but there are many. Sublimation, melting, freezing. Our three most common states of matter, this is a little bit repetitive, but we have solid, liquid, and gas. And boiling, melting, and freezing only change the phase of a substance, not the identity. So when water evaporates, it is not undergoing a chemical change, it's undergoing a physical change. What is the proper way to write out a chemical reaction? This is getting ahead a little bit, but we always write reactants first with an arrow, and then products after. And then how do I know if a chemical reaction has taken place? We get new substances. So if we ignite hydrogen in the presence of oxygen, we'll get something new, which is water. And real quick, just to mention a few ways we separate matter. If we look right here, it looks like we're using a magnet to separate iron from some sand. So that would be a physical separation. So this would be magnetism can work. This guy right here, with chromatography, we can have compounds separating based on how much they're attracted to the solvent water or to the paper here. So this is an example of chromatography called paper chromatography. Distillation is a way we separate things based on their boiling points. So if we wanted to separate, say, the alcohol from mouthwash or the water out of Gatorade, we could boil that. And distillation is another way we separate things without doing a chemical reaction. So yes, there is fire going on here, but actually what's going on with the matter in this round bottom flask is just a physical separation based on boiling points, so physical properties. And this one, of course, is filtration. Where we're separating things based on particle size. So the very small filtrate water molecules, solvent molecules can go through the filter, and then the residue will just stay behind in the filter. The last thing I want to mention is how to separate a compound. The only way to do so is by a chemical reaction. And here's a very common reaction. It's the electrolysis of water, where we use a battery to actually separate the hydrogen from the oxygen. And some of you might already be thinking, should I balance that reaction? Yes. So by applying a current, we can actually push electrons onto the hydrogen and take electrons off the oxygen. And we get a tube full of hydrogen, twice as much, twice the volume, and a tube full of oxygen. So we're getting two completely new substances by decomposing water into its elements. So in a chemical reaction, we are creating new substances, and in a lot of cases, we actually are changing the charge of our elements. All right, that's it for today. Again, if you want to speed through this, I know it's the end of the video, but that's totally good. And thank you.